Hello everyone, my name is Shayan Zamani. This presentation is a part of the work that I did in my master's at University of Calgary. Here we want to introduce a new approach for hyperparameter tuning in search-based test case generation, which is cost-effective. Let's start with the definition of hyperparameter tuning. For all the specifications in the scope of a problem, we can find the solution in the solution domain. Now, the solutions to a large number of problems in IT are addressed using algorithms like machine learning and meta-heuristics that are problem independent and can be used for all sorts of problems. These algorithms have some parameters that setting them helps algorithm fit into the problem better and optimize their performance. So a necessary section in the solution space that should be considered is hyperparameter optimization. In this study, we focus on test generation problem. Test generation is the problem of generating a number of test cases that cover the most functionalities of the code to verify them. In order to determine if the test suite is adequate, there are different metrics. Here we use code coverage as a metric to measure the ratio of branches in the source code that are covered in the test cases. One popular solution to this problem is using search-based techniques. Search-based methods are meta-heuristics like evolutionary algorithms and hill climbing that search through the solutions to find an optimal one. As an example, there is an open source tool called EvoSuite which uses genetic algorithm to maximize the coverage of the whole test suite. It means that it first generates some random test suites for a Java class and evolve these test suites to maximize the coverage. As search methods are problem independent, they have a few parameters too. Therefore, we need to think of hyperparameter optimization to optimize the solutions coming from search-based methods. Among the hyperparameter optimization techniques for evolutionary algorithms, one popular method is to use another genetic algorithm on top of the genetic algorithm itself, which is called MetaGA. Here we use MetaGA. In a previous study, we exhaustively studied the search space of these hyperparameters containing 1200 different configurations and used them to evaluate 177 classes. And also we showed that around 80% of those classes were insensitive to tuning. This means that 80% of all time dedicated to tuning was ineffective and it was a waste of budget and we didn't improve the coverage at all. So the idea that we develop in this study is to find a way to find those 80% of classes that are not worth tuning and allocate the budget only to those that are worth tuning. Our solution to avoid the waste of budget in tuning is to rank and prioritize classes so that the worthy classes for tuning rank higher and then pick as many classes as the budget allows and tune them. So we introduce a metric called tuning gain that measures how worthy it is to tune a class. Tuning gain is defined as the product of variation of coverage across all configurations and the sparsity of the base configuration. If the base configuration is similar to other configurations, it is less sparse, and if it is highly better than other configurations in terms of coverage, the sparsity and thus the tuning gain is higher. Here we train a model that uses the static metric of Java classes like the complexity of the code to predict the tuning gain of each class. We split our class set to train and test subsets, we train the model and then evaluate the model with a test set. In summary, we first extract some static features from the code and then predict its tuning gain and prioritize classes in descending order. Then, based on the budget that we have for tuning, we select a number of classes from top of the list. In research question number 1, we want to see how good we can rank the classes with the model prediction of tuning gain. We rank the classes based on the predictions of 2 regression methods, random forest and linear regression. Moreover, we compared the results with a random ordering as a baseline. In the results of this question, this figure shows the cumulative tuning gain of selected classes versus the number of selected classes. On top, the red figure shows the cumulative gain of the optimal order, and we can see that it stays up until we select 20 classes, and then it reaches a plateau, which means that there is no gain in tuning the rest of the classes with this ordering. We can also see the results for other ordering as well. here is random forest regression, and here is the linear regression. And we can see that when we select 20 classes, the performance of random forest regression is 90% of the optimal order, but other regressions are not as good. The numbers that we discussed in the last slide may not show the effectiveness of our results in practice. Thus, in research question number 2, we use the prioritization method to rank classes and select the top 20% of classes and allocate the budget to those classes only. We have 5 tuning scenarios here. In 2 of the scenarios, we select only 20% of classes, once prioritized classes and once random classes. And we compare it with 2 scenarios that tune the whole set of classes. And the last scenario is the case with no tuning. We use the meta-GA tuning method for the first 4 scenarios, but other tuning methods can be used here as well. In this figure, you can see the results of tuning with different tuning scenarios. This figure shows the extra covered branches due to tuning in comparison to the default configuration versus the tuning budgets up to 4 hours of tuning on a single core machine. As we can see in this figure, among 5 tuning scenarios, the 3 ones that find a single configuration per class are better than others. In addition, our best tuning scenario here is using metagenetic algorithm with the top 20% of classes that we predicted, where it is covering around 30 more branches than default configuration. Something that should be considered here is that here we are proposing how to spend the tuning budget, but whether the extra coverage achieved by tuning is worth the effort depends on the context of the application. If we are dealing with a more critical code base, we conclude the 4-hour extra budget is worth the extra 30 branches. Moreover, our approach is highly parallelizable, and using concurrency, we can save up to 80% of the time, which makes our approach more affordable. The other ideas that we tried after this work was using other tuning methods like differential evolution and using other subset sizes other than 20%. We also limited tuning to hyperparameters that matters most. Thank you for listening, and let me know if you have any questions.